Okay, so I thought I would do, I know you've got the key for additional question 8 from class activity 10B, but I thought it would be a good idea to just draw all this out and see if I could help clarify it a little bit. So firstly, the problem A, it says, well, first read the question, right? That's what I said to do. So it says, for the following reactions, identify the substrate, the solvent type, and the nucleophile base strength. Based on the above, predict the mechanism, SN1, SN2, E1, or E2, and draw the major product. Okay, so no help here in terms you gotta figure it all out. So let's start with A. So if we look at A, we can see that first thing we do is we want to identify the substrate, and this is a primary substrate, and bromine is our leaving group. If we look here, we look at underline right here, the methoxide is what this is, and methoxide is an example of a strong base. It's the conjugate base of methanol, which has a pKa of around 16, so we know methoxide is a strong base. That can make it a good nucleophile. We know that a primary substrate is pretty much only going to undergo an SN2 type reaction. There are conditions where this might do an elimination since the nucleophile is also a strong base, but it's most likely to undergo an SN2. You'd really need to see something like a delta here to indicate elevated temperature to expect this to undergo any kind of elimination reaction. We've also got acetone as our solvent, which is polar aprotic, which is kind of hitting this with a sledgehammer to say it's going to go SN2 because a primary substrate isn't going to form a carbocation easily. So drawing the mechanism for this reaction, recall that we have a delta positive, delta negative. This is our nucleophile. Bromine is our leaving group. So there is our product. You'd also see Br minus as a product, but usually when they say draw the product of this reaction, they just mean draw the major organic product, which is this ether right here. Okay, let's look at B, and we can see the first thing we want to do, as I said, we want to identify. We see that the substrate is a secondary alkyl halide, which opens up all the possibilities in the world. If we look here at our nucleophile, we can see it's the same nucleophile as in part A, which is methoxide. The only difference here is that it's written as sodium methoxide because they've included the counterion. But it's exactly the same nucleophile, and as we said above, it's a strong base, but this is a more hindered substrate, so that starts to open up the possibility that it is a good nucleophile, but it starts to open up the possibility that elimination could take place. So the next thing we want to look at is we want to look at the solvent, and the solvent in this case is something called DMF, and DMF is equal to a compound called dimethylformamide, which looks like this. And this is an example of a polar aprotic solvent. And so this is going to favor SN2 and E2 reactions. Since we've got a really strong base and we've got a somewhat sterically hindered nucleophile, this is primarily going to go via elimination. If I was writing this question, one of the things that I would add into it to sort of drive home the point of elimination is I would add a little delta under there to indicate that I was heating this up, which is, as we've said, favors both E1 and E2, but in this case it's definitely going to be an E2 with the polar aprotic solvent and the strong base. So I'm going to erase some stuff and draw the mechanism. So we've got 4 beta hydrogens. It doesn't matter which one of them is eliminated because it would all give us the same product. And here is our methoxide, and it's going to remove one of those hydrogens, and that's going to give us as our product the compound cyclopentene. We also end up with methanol and sodium chloride, but the product that we're really worried about is the major organic product, which is cyclopentene. And just to reiterate, remember this is an E2 reaction. We've got a strong base. We've got a more sterically hindered electrophile. And as I said, we've got a polar aprotic solvent, which doesn't help a carbocation formation. And as I said, if I was writing this reaction to further hit home, I would add some heat to make sure that I got elimination. Okay, so let's look at C. Once again, we've got a secondary electrophile, same one we had above. Now we have sodium cyanide as our nucleophile, which I've redrawn there. And cyanide is the conjugate base of a relatively weak acid, and it is a good nucleophile. So since it's the conjugate base of a relatively weak acid, it's a relatively weak base. So that means even though secondary, like I said, it can undergo SN1, SN2, E1, E2, this, because we've got this good nucleophile that's a relatively weak base, that is going to favor some kind of substitution reaction. So the question then is it going to be, SN1 or SN2? We've got a slightly sterically hindered nucleophile here, so that could form a carbocation under the right conditions, or the reaction could just go via an SN2 reaction. So then we got to look at the solvent, and recall this is the dimethylformamide, which is a polar aprotic solvent, and a polar aprotic solvent does not favor the formation of a carbocation, so this is going to go via an SN2 reaction. So, drawing the mechanism for the reaction, it's an SN2 reaction, so get something that looks like that. So there's our product, and we're also going to have as a product NaCl. But remember, one of the things we're almost always looking at here is we say draw the major organic product, and that's what that is. Okay, so let's look at question D. First thing we look at is we see that we have a tertiary substrate. So we know that SN2 is off the table. That's definitely not going to happen. But we could still have E2, SN1, or E1. Okay, so those are still possibilities. So let's look at what else is going on. Okay, so we have as our nucleophile, we have sodium. Now this is sodium ethoxide because we've got an ethyl group here. And so this is the conjugate base of ethanol, which is a weak acid with a pKa of approximately 16, so that we know this is a very strong base. And if we have a strong base, that makes it very difficult to form a carbocation. So that's unlikely to happen. So that tells us SN1 and E1 are off the table. Also, we have acetone, which is a polar aprotic solvent, which also tells us that that forming a carbocation is very unlikely. Even though a tertiary can form a carbocation, the acetone solvent is gonna make that a little bit more difficult to do. Okay, so now that we know this is likely to be an E2 reaction, let's erase some of this stuff and draw the mechanism. Okay, there's our strong base, and let's look and see where the beta hydrogens are in this molecule. There's one set of beta hydrogens, and there's another set of beta hydrogens. Notice that if we were to, so we have the possibility of two different products here. If we remove the beta hydrogens in blue, that's going to give us this compound, which is 2-methyl-1-butene. If we remove one of these beta hydrogens, we'll get this product, which is 2-methyl-2-butene. Now the question is, which of these is going to be the major product? And the major product is going to be this compound right here, because this has the more substituted alkene, therefore it's more stable. So as I said, this is the major product of the reaction. Okay, so now let's ask another question. What if I wanted to get 2-methyl-2-butene as my major product? What would I do? Well, if I wanted to get a non-Zaitsev elimination, the major product in this reaction is written would be a Zaitsev elimination. But if I wanted to get non-Zaitsev, what I'd want to do is not use a slim, speedy base like this. What I'd want to do is I'd want to use a bulky, sterically hindered base like this T-butoxide here. So this is, recall, T-butoxide, and as I said in class, it's usually written TBuOK because the counter ion is usually potassium, and so that's potassium T-butoxide. So recall from class that this bulky base, rather than reacting with these more sterically hindered secondary hydrogens, is instead going to react with the more accessible primary hydrogens, giving you the non-Zaitsev product. So if we wanted to draw that mechanism, it would look like that. Kicking out bromine, and of course you get bromide as a product as well, and that would hang out with the potassium from the potassium T-butoxide. Okay, last one in 8E. Here we have a secondary substrate. We have water, and water is also acting as the solvent. And recall, this is a polar protic solvent. So with a secondary, we could get SN1, E1, SN2. Oops. I'll leave out the SN2, E2, but since we have a polar protic solvent, that's going to favor carbocation formation, so that means it's likely to be either SN1 or E1, which a secondary can do, and that leaves out SN2 and E2. Recall also here that water is a weak base. Why is it a weak base? It's the conjugate acid, or it's the conjugate base, excuse me, of hydronium ion, which is a very strong acid. So it's a weak base. It's polar protic. It can act as a nucleophile, and it'll work with as a nucleophile definitely with a carbocation, which helps this substrate form. So as written, this is probably going to give you a mixture, or definitely going to give you a mixture of both SN1 and E1, and recall the first step in that reaction is going to be the formation of a carbocation. If the reaction is going to go SN1, water is going to act as the nucleophile and react with that carbocation to give me this protonated alcohol, and then the last part of the reaction is just removing one of those protons. That's just an acid-base reaction, and that gives you that alcohol plus H3O plus. And this reaction, where the solvent also acts as a nucleophile, is also sometimes called a solvolysis reaction. And this is where solvolysis, lysis means to break something open, and so the solvent is acting to break off the leaving group, is one way to think about that. Okay, so that's what would happen if it were an SN1 substitution reaction. All right, so let's draw the mechanism for an E1 reaction. Remember that the first step in an E1 is exactly the same as an SN1 reaction, and that is the formation of a carbocation. Now notice we have two beta carbons on this carbocation, and they're both identical, so it doesn't matter which of the beta hydrogens I eliminate. So water is going to act as the base in this reaction, and that is going to do the elimination and give us this alkene. And since they're drawn in the starting material, I'll go ahead, or in the carbocation, I'll go ahead and draw them in here. And there's that other carbon. Okay, so a question you might be asking yourself is like, oh my God, how can water be a base? It's a weak, you told me it was a weak base because it's the conjugate base of hydronium ions. So what's going on here? Well, in these E1 elimination reactions where you have a carbocation as an intermediate, these hydrogens that are adjacent to this carbocation are incredibly acidic. They are so acidic that even a very weak base like like water can pull them off. And the reason there's such a strong acid is because, think about it this way. You've got this positive charge here. It is pulling all of the electron density out of these carbon-hydrogen bonds. It's pulling them all away. It's really polarizing those bonds and giving you a really strong, it's really weakening them, and it's giving you a really strong partial positive there on that hydrogen. So that's one of the reasons that that acid-base reaction is favored. Oh, so I'm still recording, so I'll just go ahead and talk about this. At any rate, so there's your SN1 product and there's your E1 product. So you know that you're going to get a mixture of these two unless you have some additional information. So for something like that, this is definitely going to be a mixture. If you wanted to say that you were going to increase the amount of the E1 product, you would definitely have to heat it. And the way that that would be indicated it would either say heat, or there might be a little delta underneath the that reaction arrow. So that would be a way that you would figure that out.